Hello, good morning everyone. This is the oxygen session. I am Melchirre Conti, Space Resource Engineer at ESA. And today will be the session on oxygen production. I think Taylor Haines, has he arrived? Taylor Haines. Okay, so perhaps we proceed to the next speaker if my program would decide to wake up. It's not. It's not evident. Please. It's Francesco, okay. Welcome to the stage, Francesco from ASI, which will have a presentation on the carbothermal payload. You have 10 minutes plus questions, so the floor is yours.
Thank you, Melchirre. Let's wait for the presentation to come up. Anyway, just presenting myself. As Melchirre said, I'm Francesco Latini from Italian Space Agency. I will talk today about the Oracle payload that ASI is developing to demonstrate the oxygen extraction through carbothermal process from lunar regolith on the moon. Let's proceed. Let me just understand how to. How do I make the slide? Okay, like this. Perfect. So, before going into the detail of the project, just want to remark the importance of lunar, in general, exploration for Italian Space Agency. We have here a summary of the projects and programs that ASI is developing, either as national activities or in bilateral program, or under in collaboration with the European Space Agency. As you see, we have many around the moon, but something is happening also on Mars, and of course the support for all of these that we have to provide from Earth. So for those of you who don't know what Oracle is, this is as I said, the technological demonstrator that aims at validating the carbothermal process to extract oxygen from the lunar regolith. And in order to do so, we aim at, let's say, measuring the yield of the process through which we can measure, by measuring the products after the carbothermal reaction, so CO2, water vapor, and CO, and possible other products that may arise due to minerals that we find in the regolith and that can react with methane or hydrogen, as you see later. Of course, we want to see if there are any deviations from what we obtain on Earth, and we want to demonstrate the repeatability of the process to validate, of course, its robustness in a lunar environment. As an additional, let's say, objective, we would like to correlate the amount of oxygen that we extract with the type of regolith that we found on the lunar surface that we, of course, cannot know really in advance for, let's say, now. This is a slide that we have been keeping it since the very first presentation because it demonstrates how actually Oracle is developing throughout the years. And right now, so the first phase was conducted with Politecnico of Milan for phases A and B1, through which they gave some important results regarding the, let's say, the general configuration of the payload, what it should achieve. Now the contract is on the hands of OHB Italia, and we achieved an SRR last March. It was closed on March 2026. And the next step is the procurement of the service for launch and operation on the lunar surface. Okay, so as I said, the kickoff start of the contract was held on last year, almost around this time, May 2025. With OHB Italia, involving also Kaiser and Enea from Italy. The SRR gave us some important results regarding what the preliminary baseline configuration for Oracle should be. And so, in particular, we decided to end the, let's say, the validation of the process after the carbothermal reaction, because this is what it has not been done yet on the lunar surface. Since we had some discussions with possible providers, we decided to leave the regolith collection to them, so we will only provide some sort of mechanism to handle the regolith once it is received on the Oracle payload. The payload has mainly autonomous thermal control and some dust protection, of course, to avoid any, let's say, contamination earlier in the phase of, when you settle on the lunar surface. Let's say that Oracle operation will last around 94 hours, not years, of course. The products will be released in the outer environment, and the accommodation conditions will be finally discussed with the provider once it is selected. In order to select the launch provider, we are having some discussions, and the selection criteria for us are first the understanding of Oracle objectives that we gave to the providers and to evaluate, in order to let them understand what our requirements are. We want also to have a credible, let's say, way to collect the regolith from them and to give it to us. Of course, background and experience of the company, and the adequacy of the commercial offer. With mainly this criteria, we are selecting which opportunity will be the one in which Oracle will be accommodated on. The Oracle configuration is summarized in these schematics here. As you see, we have a main reactor in which we want to pour 30 grams of regolith per cycle. We aim at repeating this twice in order to assess its robustness, as I anticipated at the beginning. Let's say that each batch is heated up to 1100 Celsius degrees, so we won't reach any, let's say, melting of the batch, but we will achieve the conditions such that the mixture of CH4 and hydrogen with 15 and 85% respectively will allow the reaction with the batch in order to extract the oxygen in the final form of carbon oxides. The alternation scheme that through the help of Politecnico Milan was decided, and still is the one that we will baseline the payload for, is 2 hours for a mixture phase, initial mixture phase, and then 5 hours of a washing phase in order to remove some coke deposits that can be present and could slow the reaction. The washing phase is performed using hydrogen only. So the whole phase should last around 10 hours, and then a cool down phase starts. So this is a very very preliminary sketch of what the Oracle payload will look like. You have, can we, okay, this like this. We have a regolith handling system here where the, let's say, collection system will pour the regolith onto. Then PCU, so the tanks for hydrogen and the mixture of CH4 and hydrogen. The fluidics system, and of course, the main reactor. That's where the process will take place. Let's say that the CONOPS for the process are, you can see them here. We have a commissioning phase of 25 hours in which it will be every, let's say, valve and mechanism will be checked. The heaters, the fluidics, and everything to be sure that the reaction can actually take place. Then a first cycle lasting 24 hours. As you see here, before the first cycle, there are two phases in which we do not have provide any power, but it is zero for us, but it's not zero for the regulated providing system. And the duration of this phase is not actually something that we can decide, but it will be decided by the provider. Then cool down phase lasting 10 hours each, and after the two repetition, the disposal with the tanks evacuation for the remaining gas on the tanks. Next steps. For sure, we aim at selecting the lending provider and consolidating Oracle interfaces, let's say by the end of the year, or anyway before PDR hits. The consolidation for Oracle design for the PDR, of course, and also the operation timeline depending on lender-provider constraints. Preliminary tests will be, of course, performed to verify the main reactor behavior under structural and thermal sealing aspects. We will aim at optimizing the process parameters in order to see whether we can increase the yield somehow by adjusting some of the parameters that I've shown you earlier. At the same time, we are developing also a planogram model to perform some process cycles and calibrate Oracle payload before sending the payload on the lunar surface. And we execute some tests to assess whether the blade fluidization condition could impact the yield of extraction and how. So there was a final slide, but anyway, thank you very much for the attention.
Thank you very much, Francesco. Are there questions from the audience? Yes, please. Please, your name.
Thank you very much for the very nice presentation. All your experiments, you rely on certain kinds of simulants or regolith. As far as I know, there are no such simulants that they might contain also another chemical that is also present on the moon, and that is perchlorates. We do know that perchlorates are extremely reactive, not only that, but explosive, very much explosive. So to be certain that the process runs safely, should you consider the presentation of such potential hazards? And also, if so, to have some kind of sensors that you first check if such perchlorates exist on soil and then sample your regolith and do the processing.
Okay, thank you very much for the question. So the simulants that we use till now do not contain perchlorates, as you said, and to be honest, it is not an aspect that we've considered yet. For sure, I'll take that into account and see how we can, consider these before handling the Oracle. Okay, thank you very much.
I assume that you have a sort of degassing first step.
No, so we have, but mainly also, let's say, we were considering about having sensors after all during the process take place, of course, after the main reactor. Let's say, the analysis of the composition of the regolith is not something that is up to us till now, but we were wondering how we could evaluate which kind of regolith we have to evaluate also how this could affect the reaction. But I'll take into account this aspect and see. I'll hope to come next year with some possible answer on this too. Okay, thank you.
Thank you very much. No more time for questions. Unfortunately, I would ask the audience to keep the question short because we have only 1 minute, 2 minutes for questioning. So thank you very much, Francesco.
Thank you, Melchirre.
Very nice presentation, Francesco. Now, another system for the extraction of oxygen is Georg Poehle from Fraunhofer Institute of Manufacturing and Technology and Advanced Material with the Mini Roxy. No, it didn't. No. If you will join, we'll have to join the queue. Thank you very much.
Thank you. Okay, no presentation yet. I'll just start. Good morning, everyone. My name is Georg Poehle. I'm representing Fraunhofer IFRAM from Germany. And I hope that the presentation will appear. Okay, I can see it. And now it's there. Thank you. Okay, so some of you might have seen a presentation on Roxy or Mini Roxy at one of the previous editions of the Space Resources Week. And in these previous editions, I've mostly talked about the project on a strategic level. Today, I will go a bit deeper into things like material science and material selection. So first of all, what is Roxy? It's the abbreviation for regolith to oxygen and metals conversion, and it's a molten salt electrolysis process for the reduction of lunar regolith to produce oxygen and a metallic byproduct. It's a molten salt electrolysis that runs at 850 to 1000 degrees Celsius. And let's say the trick about Roxy is that we are using a solid oxide membrane. And this means that we will have an inherent oxygen separation and purification in the system, because the membrane is highly selective for the oxygen ions that are created. So they are extracted from the reactor before they can form molecular oxygen inside the reaction zone or cause gas bubbling. Mini Roxy is this process stripped down to its essentials to optimize the cost-benefit ratio of a demonstration mission. On the right-hand side, you can see a few impressions from that. On the lower left, we have our terrestrial testing facility where we run tests with the system. On the right from that, there's a view of the modular electrolysis cell that we're using, which we are calling a cartridge. And on top, you've got a CAD model of a potential lunar demonstrator. So of course, this kind of small and lightweight demonstration can only be the first step in the roadmap, because it cannot produce oxygen at a level you can really use. So the next thing, step by step, have to be larger and larger plants that can finally satisfy real-world or industrial demands. At this point, of course, these kinds of facilities are only present on a conceptual level and not really technical reality. For the moment, our priorities are, first of all, Mini Roxy to validate the process chemistry in space. This is supported by the UPrep method, which is a modeling method to de-risk the interaction of regolith with lunar hardware. Some of you might have seen the presentation by Thea Birch on that yesterday. And finally, for the pilot plant, as I've said, not on a technical level, but just thinking about how something like this could make sense economically. And the first analysis on this has been published earlier this year in cooperation with the Colorado School of Mines. So the nice thing about ISRU is that we can't really retreat into our nice little scientific disciplines, but we have to interact with a lot of different experts to really understand all of the different aspects of the process and the different things we need to solve. And I'm glad to say that we have a really good cooperation with Airbus, with the universities of Freiberg, Braunschweig, and Ulm in Germany, and Boston University in the US. So now I'd like to go a bit deeper into metallurgy and materials diagnostics, about some of the challenges which we have encountered when we were developing this process. So one of the main issues that we have to contend with is the cathode degradation. This is not really too surprising, because in our system, the cathode is the one component that is subject to the most challenging conditions. And if we try to sort these out a little bit, we can say that we have 5 different potential degradation mechanisms. 2 are extrinsic, so they come mostly from the periphery and the setup, and 3 are intrinsic to the system. As the extrinsic ones, we have residual oxygen, which can leak from the anode side, or at least in the terrestrial setup, can come from the environment. And we have residual moisture that can either come from the electrolyte or from the regolith that we are introducing. Now these factors can of course be controlled, they're relatively predictable, and you can take countermeasures against them. However, there are also intrinsic factors that are related to the regolith, the reduced regolith, and the molten fluoride salt that we're using for our MSE process. These, of course, cannot simply be removed, and so we need to find a material that can withstand these conditions. And when we approach this problem with a combination of test and analysis, we can see that although there's a large number of candidate materials, there are actually very few that can withstand the conditions that we actually encounter. Going a bit deeper into this, if you think about high temperature stability and stability to chemical attack, you would of course think of the refractory metals, and we've worked with those for a long time. However, there are two problems. The first thing is, if there is residual oxygen moisture, we can get a problem because the corrosion products of these materials can disturb our process. Now, this can be controlled to a certain extent, but we can also see that we have detrimental interactions with a reduced regolith that once again affect the reliability of our process. Second one would be noble metals would be very nice, and we could show that they are highly resistant to the molten fluoride salts, and things like oxygen and moisture are of course no problem there. However, once again, the formation of alloys or intermetallic phases mean that these kinds of cathodes wouldn't be stable and would have to be regenerated all the time, which doesn't make for a very good system. And finally, we have what I broadly call compounds here. We have particularly looked at zirconium nitride, molybdenum silicide, and a composite called MOSIP to see if they can fulfill the conditions. Going a bit deeper into some tests, here are some failure mechanisms and the countermeasures. So for the extrinsic ones, with appropriate pre-treatment of the electrolyte that we're using, we can reduce the level of residual moisture in there from almost 0.5 mass% to a level that's not detectable any longer in DSC TGA. And for oxygen, we can use things like solid-state getters, which can protect the cathode materials. This is shown on the left-hand side down. The upper picture is molybdenum sheet metal without getter protection, and the lower one is with getter protection. So on the right-hand side, you can see that intrinsic materials are more challenging. For the molybdenum cathode, we can see that salt exposure leads to the release of corrosion products that then form some kind of a slag on the salt surface. And on the bottom, we have some exposure tests with the new materials, and I will go into more detail on this on the next slides. So first of all, we had some salt exposure tests with the materials, and the good thing is that we could see that molybdenum silicide and MOSIP seem to be largely inert towards that. For zirconia nitride, we see some minor discoloration, but no real attack, formation of large corrosion product layers, or leaching of materials or elements from these materials into the salt. The same goes for testing against the regolith in the oxidic phase, although this is not so surprising because we would expect these materials to be mostly inert when it comes to oxide minerals. The more challenging test is, of course, the exposure to metals or reduction products. In this case, we've taken the road of a challenge test, so we've mixed the materials that we would expect to be created by the reductions, such as the metals titanium and iron, and also silicon, and then brought them into direct contact with the materials. In reality, this might look a little bit different because the contact might not be as direct, the composition and therefore the activity of the elements might be different. But I think this challenge test can show us what kind of reactions we have to be aware of. And in this case, we can see that for zirconium nitride, we have two warning signs. The first is a formation of a reaction layer that is composed of zirconium, titanium, and silicon. And we can see the formation of this needle-like phase on top that is also formed from a reaction between the materials and the cathode material under test. For the molybdenum silicide, it looks a little bit better. We only have a very minor reaction layer on top, but something we can see is that along the grain boundaries of this material, titanium and aluminum penetrate. We think that this might be related to the way of manufacturing, which was hot isostatic pressing, but it's still something to look out for. And finally, for MOSIP, we have the formation of a layer on top that is very similar to molybdenum silicide. However, in this case, we do not see any penetration of titanium and aluminum, which is one more piece of evidence that the problems we see here might just be related to the way the material was manufactured. So the next steps, which we want to do with quite a bit of urgency, is to go on, particularly with molybdenum silicide and MOSIP, to validate their performance and also their compatibility with the rest of the cell under actual electrolysis conditions. We are looking at the manufacturing technology we need to produce the porous cathodes, which we use for mini ROXY. And in parallel, we are also testing 2 other design approaches, which I unfortunately can't discuss due to IP reasons right now. And with that, I'd like to thank you, and I'm, of course, interested in your questions.
Thank you, Georg. Are there any questions from... Yes, please. A microphone here. Please keep it brief so we can have more questions.
Thank you for the amazing presentation. Can you explain a little bit more about how this is scalable if an astronaut is on the moon and they have to try to figure out how to fix the membranes with their gloves?
Well, the idea would be that they don't have to fix the membrane. The membrane itself is a ceramic material, as a solid oxide membrane, and ideally we will have it at a degree of stability where it can run for a long time, and then only needs to be exchanged wholesale. So I don't really foresee people actually reaching into the reactor and trying to change only the membrane, if that's what your question was about.
Thank you very much. Another question? Timon?
Hey, Timon Schild-Edrick, thank you for your presentation. For your test with the metals, so you said you were just using mixtures of off-the-shelf metals. Is this just going off the composition of the regolith, or is it actually coming from the analysis of some reduced products already?
In this case, it comes mostly from the analysis of the regolith that we're using, because a reduction can go to, let's say, different stages of the deoxidation. You can have some residual oxides, and what we wanted was some kind of a challenge test where we have everything that could be the worst case, or maybe the best case if we look at reduction, and then see what we would have to expect from that.
Okay. Yes?
Yes, thank you for the presentation. Did you already have a look on the properties of electrical conductivity or electrochemical behavior after the cathode, for the cathodes after the corrosion?
We have not done this yet, so there are clearly conductive materials at the beginning, and then we're mostly looking out for things like surface layers, which might have a ceramic character and might therefore block conduction. But so far it seems that what we've seen here is mostly the formation of layers that would still be conductive.
Okay, thanks.
Okay, thank you very much. I have a bunch of questions, but I'll ask them tomorrow at our meeting. Okay, so next person is Francisco Guerrero-Gonzalez from Man Electric. Will present the pre-testing of an FFC molten salt electrolysis reactor bedboard for lunar oxygen extraction. Yes.
Perfect.
Yep.
Hi, everybody. Actually, it's good that we just had the presentation before because I didn't have so much time to go into details into my slides, so that way you will be already aware of the challenges because we are doing something very similar, but for a different process. Let's start a bit with who is Mana. So basically, Mana is a Luxembourgish company founded in 2018, so already 6 years old, and it's always been positioned at the intersection between space resources and energy, particularly solar energy extraction. Today, I want to focus a bit on the work that we are doing for oxygen extraction, particularly under an ESA contract, and how we are looking into again, material compatibility, but also other technologies that have to be developed in order to have ISRU systems, ISRU demonstration missions on the moon. A couple of words about the process we are looking into, FFC process, also a molten salt electrolysis process, a bit different than the ROXY process that my colleague from Fraunhofer presented. In this case, we are working with molten chloride salts, which of course changes a bit the chemistry related to related to material compatibility. We introduced the regolith in solid state, pressed, sinter. It can be in different forms and connected to a cathode current collector. And then we start passing current through it. In this case, we don't have a membrane. We use a solid material as an oxygen-evolved anode, as an inert anode. That's also one of the things that we are looking into. All this difference between molten chlorides, molten fluorides, we have just published a paper reviewing all of those different processes in the Journal of the Electrochemical Society. So I encourage you to take a look to that, to go a bit deeper into the differences. Also a bit of context about the project itself. So basically we are working towards de-risking a potential future demonstration mission. ESA is of course the customer. The activity is led by OHV, with OHV UK being in charge of all the systems engineering and also the payload development. University of Leicester looking more into the development of the solid analysis instrument, so having an instrument that is able to look into the solid regolith before and after the reduction. Open University looking into the instrument for the gas analysis. University of Glasgow providing the testing facilities for the breadboards. And Metallicis working also on the FFC process more from a scalability perspective. So the goals for the activity are basically, as I said, de-risking the technologies and also test all these technologies in relevant environment. This means dusty thermal vacuum chamber up to TRL5. What MANA is doing within the consortium is taking care of all these de-risking activities and also is taking care of designing the reactor subsystem. Regarding the de-risking activities, we have two sides. One is reactor materials, so everything to do with electrodes, everything to do with vessel materials, reactor insulation, etc., but also looking into critical technologies. And I apologize beforehand if I cannot go a lot in detail into what we are doing, but you can catch me later if you are interested in any specific problem. The first one of those, again, inert anode, we already heard about that in the previous presentation. In our case, we are looking into refractory metals, molybdenum, tungsten, but also nickel alloys. We already saw that molybdenum, tungsten, for example, they are very brittle. And while we are also concerned about chemical compatibility, we are even more concerned about the thermomechanical compatibility. Molybdenum, tungsten, tend to break pretty easily. They are brittle. We had already experienced a bit also with ceramic materials and so similar behaviors. That's why we have seen that one of the most promising materials is nickel alloys. Of course, there's a bit more of material transfer between the reduced regolith and the nickel alloy components. But that's something that, at least for a demonstration mission, we have learned to live with. All these materials are being tested in some of the lab scale reactors that we developed in-house. And for that, with those reactors, we are also testing the inert anode materials. So in this case, we have been looking into a broader span of material types, from iridium, so precious metals, to ruthenium perovskite composites, to nickel ferrite cermets, and also a bit more known in the literature, the behavior of doped tin oxide, more as a reference material, the same as for graphite, more as a reference material to see how the other candidates behave. The materials have been produced by Fraunhofer, IKTS, and yeah, sorry for the picture. They are actually three different materials. They all look the same, but in reality, from left to right, you can see doped tin oxide, the calcium ruthenate. In this case, we are mixing the calcium ruthenate with calcium titanate in order to improve manufacturability. Although calcium titanate is not electrically conductive, it helps a lot when you are sintering the material and to keep it cohesive. The smaller one is nickel ferrite cermet. So basically, we are taking nickel ferrite and mixing it with metallic powders. And with this, we are able to also enhance the electrical conductivity. So all these materials are actually now in the lab being tested, and we will have results in the coming weeks, basically. No? Yeah. More from a technology de-risking and not so much looking into materials. We have the reactor sealing. At the end, for the FFC process, we have an inert gas, which is basically moving away the oxygen produced from the reactor. And it's also helped us to keep a pressurized atmosphere so that the calcium chloride, the electrolyte, doesn't evaporate. We have been looking into two kinds of materials for the seal. One is elastomers, and the other ones are metal gaskets at different temperatures, at different load conditions, but also in the presence of dust. So we took the finer fraction of regolith simulants below 200 microns. We contaminated both the O-ring slots, but also the knives for the metal gaskets, and we checked the performance for different cycles. We have seen that even at higher temperatures, the elastomers actually behave quite well. The metal gaskets were a bit more tricky to work with because they have to be resettable. And in this case, that's why we are going to go for the future phases with elastomers that can work at higher temperatures and also provide a lower leak rate. Maybe as a last and also important is looking into high temperature lightweight insulation. So we are working with processes around 950 degrees, slightly higher, slightly lower. And for demonstration missions, the power budgets are always very, very limited. So we started looking also under these activities into silica-based microporous materials. And as part of this contract in particular, we have been looking into how salt vapors affect the thermal conductivity of the materials itself. So you can see in the plot here on the right that there is not a huge difference at lower temperatures. So salt deposition doesn't affect the thermal conductivity of the material much at low temperatures, but as soon as you reach the melting point of calcium chloride, which is around 770 degrees, you see a bump of around 50% increase in thermal conductivity. This is basically because the vapors that accumulated and migrated through the microporous material, which at the end, as it says, it's porous, start melting and start filling the voids that are usually filled by vacuum or by an inert gas, and start increasing at the end the solid conduction through the material. So yeah, these are a couple of the things that we have done. The next steps are basically going into the reactor breadboard design with all the lessons learned from the de-risking campaign, going into reactor breadboard level testing, so functional testing. For that, we will be using our dusty vacuum chamber in-house that we have developed for this, but also for the internal R&D activities that we have. And from there, integrate this breadboard with additional subsystem. I was mentioning the solid analysis instrument, but also all the pre-processing steps that you need. And finally, testing in DTBC in Glasgow, planned for the beginning of next year, basically. And with this, I come to an end, and happy to answer any questions.
Thank you very much. Any questions? Yes, I see. Let's go with the end in the last row. No, the last row. Went up as median before.
Hello, thank you for your good presentation. Matteo Curso, University of Bologna. I'd like to ask, I saw that you are working at pretty low pressures, and for the regolith, for the fused regolith processes, there have been a few publications that highlighted that the regolith, when it is fused, it tends to climb the reactors of the wall. I'd like to ask if you also, with your mixture of the electrolyte, experience the same or not to date?
So, I think 2 points here. One, the reactor pressures that we are looking into are between 10 millibars and 100 millibars. And the second one is our process is molten salt electrolysis. So the regolith in reality is kept in solid state. We are not working with molten regolith electrolysis, and that's probably what you are mentioning that you see because of the Marangoni effect climbing in the walls. In our case, is the salt, the medium that it's molten. We have not seen any climbing similar to what you expect for Marangoni effects.
Okay, thank you.
Thank you very much. The gentleman in the first row.
Thank you very much for the presentation. Andreas Dietz from Fraunhofer IST. You mentioned that your electrolyte is molten calcium chloride, and the electrochemical potentials from the oxygen evolution and the chlorine evolution are very close together. That's a great problem in terrestrial chloralkaline evolution. Have you ever seen the chlorine evolution at the anode, and is it a real problem?
Yes, it's actually a real problem. For example, I didn't show results on iridium, but we have seen that most of our iridium getting consumed just because it's getting chlorinated. And it's at the end chlorinated and dissolved into the electrolyte. So it's a problem. It's one of the challenges of working with chlorides. And it's one of the biggest challenges, particularly for inert anode development or oxygen evolving anode development.
Okay, thank you.
Okay, thank you very much. We don't have time for any other questions, so if you have any question, ask Francisco. Separately, the next talk will be Alex Ellery, Professor Alex Ellery from Carleton University, Canada, Hephaestus, a lunar issue technology demonstrator payloads of a full manufacturing facility.
Okay, thank you very much. I don't know why I'm talking in this session, because I'm not going to be mentioning anything about oxygen evolution. Okay. That's not... Where am I supposed to point this to? There we go. Okay, yeah. Okay. So I want to talk to you about a concept we've been working on. It's not built, it's not designed yet, but it's based on a series of hardware experiments we've done in-house at Carleton University. So what we've done is, what we've been trying to demonstrate is to take lunar regolith or simulant and then basically process it in various ways that I'm going to talk about in a moment, and end up with 3D printing an aluminium tank or some kind of aluminium article, basically directly from simulant, to show a full manufacturing chain all the way from raw material to final product. So basically this idea, Hephaestus, will demonstrate basically, I won't talk about the mining part, but refinement, extraction, and fabrication of aluminium products from lunar regolith. What we're trying to develop is some kind of black box. The reason why I mention black box is because we're trying to create this environment which is fully controlled and developed and tested and so on. As opposed to when you're talking about trying to extract things like water ice, there are a lot of unknowns, a lot of parameters which are unknown and difficult to pin down. Hephaestus will be a single-shot device, basically to demonstrate a single process, a single mechanism to minimize the plumbing complexity of recycling everything and so on and so forth. I'll talk about the pictures in a moment as we go through. So within the black box, we have 5 consecutive processing stations. So we have a particle sieve, magnetic separator, HCl leaching unit, a molten salt electrolysis unit, and then a laser powder bed 3D printer. And I'll talk about these individual stations as we go through. One of the most challenging aspects is that as the sample goes through these processes, it morphs into different forms. And that creates very high complexity in handling these different forms as we pass from station to station. Basically, fundamentally, we're going to be, what we focused on is an auger, which basically translates the material sample from one station to the next, and then pass it into a hopper. One of the things we're still open about is how do we interrogate the sample as we process it. We want to use the same sensory technique, the same instrument to monitor the process as we pass through each individual station as we go along. And the two techniques we focused on, one is Raman spectroscopy and the other one is LIBS. Well, we haven't done very much on LIBS. We have developed an in-house Raman spectrometer, as you see there. And so we've been using this to analyze the sample at different points. So we focused on, many of you will be aware that everyone and his dog has been working on ilmenite processing. We've decided to focus on northite, which is obviously from the highlands. And what we want to demonstrate is that we can take a northite after we've pre-processed it, and we can extract 100% of the material. So the products we get are calcium chloride salt, which feed essentially into the molten salt electrolyte. We have silica, from which we can actually generate optically transparent fused silica glass, and possibly piezoelectric quartz, and glass fiber thermal insulation. The alumina itself that we produce is a ceramic which can be used for various refractory purposes, including the crucible that we use in our molten salt electrolysis unit. And aluminium metal, of course, which is actually a highly multifunctional material. And then finally, we also have water and oxygen, which is consumables which we produce. So what we're doing is we're taking the northite and extracting 100% of it and utilizing it with zero waste. All the reagents essentially are recycled. And this is really fundamental to any kind of, if we want to have a sustainable system on the moon, we need to ensure that we can do things like recycling. There are also some terrestrial applications for this, which I'm not going to talk about now because I see I'm running out of time, where Canada currently imports all its bauxite and then uses that to produce aluminium. But Canada is also rich in northite deposits as well, so we can utilize that locally. I'll just skip over the beneficiation. We actually used a very simple technique for beneficiating here. We just simply used a magnet to separate out from LHS1 the iron component. And this is really the core of what we did was basically we used HCl leaching, and it was a two-stage chemical process. As you can see here, we used a northite, we then leached it with HCl and water, and that produces essentially calcium chloride in solution, aluminium chloride also in solution, and then precipitates out the silica. We then removed that and dried it, and then we basically then processed, we basically roasted we sparged the aluminium chloride initially, and then we roasted it at 250 degrees C, and this basically liberated HCl gas and water vapor and left us with aluminium oxide. We then further heated it further to dry it and purify it a little bit more. But notice also that the HCl is essentially recycled largely, apart from that which is incorporated into the calcium chloride. This is actually a very general process which we could potentially apply to other lunar minerals. And I won't go into that now, but potentially we could apply it to leaching things like forsterite, lunar forsterite. So this is our MSE unit, which we built in-house. So the alumina would be then augured into the molten salt unit. We used a molybdenum cathode, and we actually, again, the reason why we didn't evolve oxygen is because we used a graphite anode and produced CO2. And this actually resulted in 95% pure aluminium metal, as you see at the bottom there. We then subjected this aluminium that was produced we found that the 95% was too brittle to draw into wire. And I'll be talking later on today about this particular issue. We used, because we had access to electron beam additive manufacturing facility, NRC, we basically took aluminium and then 3D printed it directly into a small cylindrical tank, as you see here. So there was a break in the chain, but it illustrates as well that because of the 95% pure aluminium that we produced was too brittle to draw into wire. So because we were using EBAM, this was necessary, and that was the break in the chain. However, what we intend to do is take our 95% pure aluminium and overcome the ductility problem by ball milling it into a powder and then utilizing basically laser sintering to produce as our alternative 3D printing technique. So that program is in process. We have the ball mills, and we have just recently acquired a laser printer or a laser welder, which we'll be integrating into a printing unit. So we hope to be doing that over the next few months. I'll leave it there. Thank you for listening. Sorry?
We have a few more seconds to go.
Okay.
All right. So, any questions? Timon?
Hello, Timon Schild-Esrik. Thank you for your presentation and commiseration on the brittleness of the product. That's something we face as well. About this 95% pure aluminium, what are the 5%? Is it residual oxygen, or is it kind of other contaminants?
No, it's not oxygen. It's various whatever's left after we extracted the iron component. I think it's like things like little bits of olivine, magnesium, and a few bits and pieces like that in it.
Okay. I would assume also a bit of calcium
yes,
ending up in the...
Yeah.
Calcium is not a friend of ductility.
No.
Any more questions? Advenit? Sorry, the gentleman in the front. You can ask your question afterwards, Advenit.
Well, Jun Shimada from JAXA. I have a question regarding scalability. What do you think is the biggest challenge to scale up the system in the future?
We haven't thought about turning it into a plant. My view is that I think before we start talking about plants, sorry, Mel, but I think we should be putting a demonstrator onto the moon first. I think, a small-scale demonstrator just to prove that it can be done simply with minimum plumbing. And then once we've demonstrated that, then we should start thinking about how to develop that into a scale plant, I think. We haven't really thought about that too much.
All right, thank you.
Advenit?
Advenit Mackay from the European Space Agency. What's the yield of your process to extract the calcium chloride? How much anorthite do you need to put in?
11% aluminium from a theoretical 14%.
I mean, to get the calcium chloride.
The calcium chloride. I can't tell you. We focused on the aluminium actually more than anything else. The calcium, we actually left it in solution. We didn't actually use it directly. So I can't answer that question.
Okay, I think we ran out of time. If you have any other question, please reach out to Alex during the breaks.
Thank you.
Thank you very much, Alex. The next speaker is Lucas Brian Christen from the University of Tokyo. Calcium and aluminum enrichment in lunar regolith simulants by laser-driven selective vaporization.
Okay, yeah. Good morning, everyone, and thank you for the introduction. I'm happy to share some of our research done at the University of Tokyo on the elemental refinement of lunar regolith using vaporization. And it's fairly similar to what we just heard, but it would be a reagent-free or consumable-free counterpart to that. And our long-term goal is to produce aluminum on the moon from raw regolith using thermal reduction, so without reagents. And however, in order to do that, we find that we need to first produce an aluminum-rich feedstock from regolith. And that is where the vaporization comes in. We're interested in highland regolith due to its higher content in aluminum oxide. And the idea is to put that through a heating stage under vacuum at around 2000 Kelvin, triggering the vaporization of the then volatile species, essentially reducing the oxide content within the melt, eventually leading to a residue that is highly enriched in aluminum oxide, also calcium oxide. And today I have 3 topics I want to shortly talk about. First, some vaporization experiments using laser heating, and then second, a numerical model to complement these experiments, and then third, we can derive sort of metrics for a potential ISRU plant. And here we see the experimental setup. This is the vacuum chamber. It's a 20-liter vacuum chamber. We place the sample inside, have a continuous wave laser irradiating from the top right here, which is up to 1.5 kilowatt in power at 1080 nanometer. And then we measure the surface temperature here through this vertical path and lead that information back to the laser to, via PID control, control the output power to maintain a constant surface temperature. And then through continuous pumping, we achieve a pressure of 70 Pascal inside the chamber in this experiment. And we used, 2 materials, LHS1 and anorthosite, mainly because they both share a high content in silicon dioxide, and this is the species that we are mainly vaporizing through this kind of process. Here's another image of the setup. We have the vacuum chamber here on the right. That's the 20-liter vacuum chamber, the fiber laser, the temperature measurement path, and then here's the close-up of how we position the sample inside. That's this rectangular block is the cooling block with the tantalum plate on top that is removable, and then the sample that is irradiated by the laser. And our result of that is seen here. We have some video snippets as well of these 2 materials. But most important parameter is here the vapor rate, so the mass loss over time, and as well the laser intensity, so how much power do we need to input to maintain a constant surface temperature. And we have to say we try to maximize the surface temperature on each sample because we want to maximize the vaporization rate. So they're a little bit different here. And additionally, we have to treat these values a little bit carefully because the laser spot diameter in this experiment was 6 millimeter. The temperature measurement was at around a 5 millimeter spot. And because the laser has a Gaussian profile, the temperature distribution is non-uniform, and that is not accounted for in this data. And this is really... We can also plot that, just the relative total mass on the y-axis over time. So the mass loss is what we see here for LHS1 in blue, is a little bit faster than anorthosite, is exactly what we would expect. And we see this was only performed until around 1% mass loss. And that already took quite a long time. So in order to complete this kind of curve, we now take a numerical model to finish that silicon dioxide depletion. And then for the model, this is the flowchart that you see here of the model. It's a simple code in Python, nothing spectacular. We calculate the equilibrium vapor pressure of the vaporizing species using the database, NIST-JANAV. And from there, we go ahead and scale that vapor pressure, saying that the flux of that species, the vapor pressure, only depends on its molar fraction within the melt. So that would be an ideal solution. The activity coefficients are just simply 1 in this case. And then we can go ahead and calculate the vapor flux of each species and sum that up using the Hertz-Knudsen-Langmuir equation with this ideal solution. And that iterates through time steps until we reach a silicon dioxide content of less or 1 weight percent. And yeah, then we go ahead and end that iteration. And that gives us the oxide species flux over time, and we can plot that.
I think we need new
Maybe the battery?
batteries.
I'm not sure. I'm trying my best here. Anyway, thank you. So I'll just keep that. Yeah, so we can plot that macroscopically now. Again, the total mass on the y-axis and x the time, and we see that we deplete until, so these curves end at 1% of silicon dioxide left inside the residue. So we have around 40% left at the end of the initial mass, and these curves, are represented for 10 Kelvin steps for each material, LHS1 and anorthosite. It's composition dependent, of course, and we can plot our experimental data here between these lines. This is a zoom of the very early stage here of that model. And what we did next is we took the two nearest lines and interpolated using our experimental data and the numerical data to kind of complete that vaporization path numerically that we would achieve likely if we were to continue that experiment for 30 plus hours. And what we can then do is extract next page please. Yeah, extract these interpolated curves, which is in blue for the LHS and in orange the anorthosite. And what's interesting about this, we can now know, one next please, we can now know the energy consumption that we need to, the energy consumption that we need to put in to derive that total mass until we reach 1 weight% of silicon dioxide in the residue. And that would be the specific energy consumption. We reach values around 10 megawatt hours per kilogram, which is quite high of a number. We have to say that likely they were going to be lower because in this experiment, because this value depends on the laser input, the data that we got from the experiment, and that is likely overestimated because we used a cooling plate in the experiment, which draws additional power, that accounts as a loss basically here. And now we can go ahead and say what effect does that have on a potential solar plant, ISRU solar plant. For example, now that we know the specific energy consumption, we can derive how much of solar light, if we were to use solar light, how much do we need to collect an area to provide that amount of energy if we define a can we go one back? I don't know how that works here. If we define a production target of 1 kilogram per week, for example, we find that we need to collect solar light in an area of 30 to 90 square meters. That would be one of the metrics for a solar plant in that sense. We have another constraint, that is flux. We have the required heat flux in that equation on the left side is equal to the losses. That would be the vaporization cooling effect and the radiation cooling effect. And the radiative loss is scales with the temperature to the 4th power. So there's a high magnitude there that we have to account for. And the total heat flux going out from that equation we can calculate. And if we were to use solar light, then we now know that we have to at least scale that solar light concentrated down to 570 times onto a spot. And as a summary and conclusion, I talked about the calcium aluminum enrichment, and from a physical point of view, it is feasible. Energetically, it's a different discussion at this point. We can enrich and change the composition of from a previous original content of around 25 weight% of aluminum oxide to finally 65 weight% of aluminum oxide. And then we can go ahead and derive some metrics for an ISRU plant. And we saw from this discussion that radiative recycling is essential for such a reactor. So we have to utilize some sort of reflective shielding inside the cavity or re-radiative shielding. And that would be the end of my talk. Thank you very much.
Thank you very much. Quite interesting. I already see the hands up in the front. Two hands up in the front. Let's start with the gentleman on the left.
Thank you so much. Amazing presentation. Very, very informative. This is Sujit from Public Access. I wanted to find out what challenges did you face with regards to the vapor pressure difference and any occlusion which might have happened of the lens in the experimentation process?
On the window?
Yes.
Yeah, that is definitely a factor. About the vapor pressure, I mean, it's not a challenge. It's due to the gap in vapor pressure that we're able to do this sort of refinement. The window is affected definitely by vapor deposition. So one approach that we would like to implement, we didn't do it here, is to have some sort of purging with argon gas, for example, near the window. In that case, it's just a window in this chamber. But yeah, that's definitely an important issue. Yeah, that we do not accumulate deposits on such a optical element.
Alex?
Yes, not sure if I understood something. You're using your laser as a representation of the solar concentrator, is that correct?
In that sense, yeah, that would be the
Okay. Point. Is there any reason why you didn't use the solar concentrator directly in your experiments?
Short answer, no. Okay. We could exchange for solar light. We're interested in laser application. That would be an answer. And from this discussion, we see that this kind of reactor potentially scales better with a laser than solar light.
Okay, that makes sense. Thank you.
But also, what I noticed is the amount of energy that you need to deploy is not. Have you thought of a method to justify the extra consumption versus the mass of non-consumables of other processes that you would have to take with you? Because clearly, whoever looks at that mass energy balance goes, whoa.
Yeah. No, we're just hoping for a endless energy supply.
Okay.
Potentially a nuclear reactor. We never know. But yeah.
Okay. Sorry, we are out of time for questioning, but you can catch up with Lucas and Brian in the break.
You so much.
Thank you very much. The last speaker, who was the first speaker, is Tyler Haines, Added Value Solution, AVS UK Ltd, Oxygen. Novel payload for oxygen extraction from a lunar regolith.
Hi, good morning, everyone. My sincere apologies for any disruption I caused earlier. I'm glad to be here. I've managed to find the most inaccessible hotel in all of Luxembourg, so please forgive me. Thank you all for being here. My name is Tyler Haines, and I'm representing AVS as a mechanical engineer, and I'm here today presenting Oxygen, a novel payload for oxygen extraction from lunar regolith. So I won't go into too much detail on the importance of extracting oxygen from local resources on the lunar surface. I'm sure we've heard a lot about that. Anyway, so really the importance of extracting oxygen on the lunar surface is not only for sustained lunar operations, but also to support future missions, deep space missions, as a halfway house. So just to give you a little background on who we are at AVS, we're an international company developing high-tech solutions in industries from space to nuclear. We have bases in the US, the UK, France, and we're headquartered in Spain. I'm based at our UK branch, where we specialize in spacecraft mechanisms, control electronics, and control electronics and embedded systems as well. We've also recently moved into a new building that also houses some state-of-the-art design and AIT facilities. So for us, that's a big move, and we're really excited about that. Some of our most notable recent projects include the development of a universal tool changer for the Argonaut lunar lander, a modular, flexible solar array deployment mechanism as part of the UKSA's ROLA project, as well as a thruster pointing mechanism, which is soon to be launched on ESA's upcoming Henon mission. So we're really proud of that. Also, our team has developed some competency in ISRU technology over the past couple of years, working with some industry leaders on several projects regarding oxygen liberation from lunar regolith. So just to give you a little bit of background on the Oxygen project, it is an international project funded by the UKSA with technical inputs from my colleague Alex Ellery and his team at Carleton University in Canada, as well as Glasgow University and obviously AVS UK. And the aim for our project was to essentially develop just a high-level concept for the minimum viable payload for extracting oxygen autonomously on the lunar surface as a technology demonstrator. The baseline that we chose for the process to actually liberate oxygen was molten salt electrolysis. Of course, there are a number of different means of liberating oxygen from lunar regolith, MRE, or molten regolith electrolysis, and molten salt electrolysis. We have some experience with molten salt electrolysis, so that is what we decided to go with. I'm sure you have a pretty good understanding of molten salt electrolysis already, but just as a refresher, essentially what we do is we submerge molten regolith in a molten salt bath and essentially pass a voltage across that and an electrode, decomposing the sample and allowing us to capture the liberated oxygen. So we needed a starting point, and so in order to develop a basic set of rudimentary requirements for our payload, we settled on choosing or selecting the Intuitive Machines Nova-C lunar lander as a sort of payload baseline. And you can see on the right-hand side there a sort of relative size representation of the oxygen payload with reference to the lunar lander itself. Some of the important aspects of the system, there are several subsystems. I'll only go into a couple in slightly greater detail in this presentation, but this includes an acquisition subsystem, which transports lunar regolith from the lunar surface, up to a pre-processing system, which both filters and then deposits that sample into an electrode assembly, which is then submerged into a electrolysis unit, or a reduction subsystem. Subsequently, we have the analysis subsystem, which detects and measures the oxygen liberated from that process. But basically, what we have, the Nova-C lunar lander has I think a peak power supply of around 200 watts and a peak payload capacity of about 100 kilograms. We were a little bit greedy in setting out our initial requirements, setting aside a payload budget of 50 kilograms and 100 watts of peak power, with the intention to produce a 10-gram sample of lunar regolith over a period of 20 hours using a single-shot device. So this is a sort of high-level view of the integrated pre-processing system and reduction subsystem. What you see there on the left-hand side is that integrated system in the open and closed configurations. And on the right-hand side, you can see that we've actually built some functional hardware. So the development of functional hardware was actually a key aspect for us in this project. Anyone can look at this current design and see that there's a significant amount of work involved in translating that design into something that is flight compatible. Now, we understand this, but we felt that in order to make significant progress in the time that we had, developing functional hardware and testing that in a scenario that is representative of a mission was something that could likely lead to significant progress in the short space of time that we had. Taking a closer look at the sort of reactor vessel itself, on the right-hand side, we can see a section view of the pressure vessel subsystem, in the center of which you can see our crucible, which contains our molten salt, around which is a Inconel sheathed resistance heater, and surrounding that we have thermal insulation. This is a high-performance microporous insulation, which is encased in an Inconel shell, which forms the main body of that vessel. So Once the system is actually loaded, the preprocessing system actually loads the electrode and the regolith sample into the vessel itself, sealing the vessel. The vessel is then powered on, but prior to that is charged with an argon atmosphere up to 1 bar. The reason for that is to mitigate salt evaporation. Once that happens and the salt is up to around 950 degrees Celsius, the electrode assembly is then energized, and we expect, obviously, to produce oxygen over a period of roughly about 16 hours, liberating around 60% of the oxygen contained within a 10-gram sample. On the left-hand side, you can actually see how compact the system is, and really one of the principal drivers behind the size profile of the system is the regolith sample size itself, with subsequent system elements forming consecutive layers building outward from the core. So I just wanted to show you some of the actual hardware demonstration or testing that we did alongside Carleton University and Glasgow University at their facilities up in Glasgow. In the left and central frames, you can see the sample acquisition systems, which our partners at Glasgow worked on as part of the project. And on the right-hand most frame, what you can see is the actual integrated testing of the sample acquisition system and pre-processing systems working in tandem, all performed within Glasgow University's dusty vacuum chamber. I don't know why that video isn't actually playing. Oh, it is, sorry. Forgive me, it's just very slow. But that was actually, these tests were actually performed in Glasgow University's dusty vacuum chamber under vacuum conditions. So what did we learn? I mean, specifically with regard to the mission profile itself, I think we actually were able to develop a concept architecture that we think is viable in terms of the sort of mission that we had envisioned for oxygen. Is the architecture scalable? I think in principle, yes. But however, scaling the architecture and into something that is a truly continuous process is not only challenging, but is based on identifying crucial materials that make this a sustainable process and one that is robust and reliable over long periods of time that does not degrade in performance. Again, the search continues, as you've heard from my peers, the search continues for viable anode and cathode materials. This is a significant area of interest and also of rigorous research within the MSc topic itself. We identified key areas for development and optimization, but essentially we were able to develop a system that we think, at least conceptually, could fly. So what does the future look like for us? Well, Avius, as part of the development in the project, actually developed a prototype reactor that you see there on the right-hand side. This is meant to be used as a test apparatus, testing not only different materials, but different internal configurations, and is a function, in the internal aspects of the reactor itself are functionally identical to that proposed within the oxygen concept. Transition to continuous architecture is difficult. Optimizing the electrolysis process and by increasing the reduction time and increasing efficiency is part of the main goals for the future. Thank you very much. That's all I have for you today.
Thank you very much. Any questions? Yeah, Georg.
Thank you for the talk. I have one question about your electrode setup. So if I understood it correctly, you've got the spring in there that is pressing down on the cathode.
That's correct.
And that will be submerged in the electrolyte and subjected to the electrolysis temperature. So what kind of material would you imagine for that spring?
So because we're using a single-shot device, we feel that some sort of nickel superalloy should be more than sufficient, at least to survive that process. In our original, some of our original designs, we use stainless steel. Of course, this degrades quite rapidly over time. But because it's a single-shot device, we don't have many of the same worries, but that also means that that particular philosophy is not scalable.
I see. Thank you.
Sure.
Any other question? Advenit?
So the test for your sample acquisition system, so you say you run it in vacuum. What sort of simulant did you use? Because it looks very round and regular.
Oh, so in one of the videos, what you saw was glass beads being used as part of the auger system, as well as the pulse elevator. So that was just an example to show you some of the actual hardware that we developed. But in testing the integrated pre-processing and acquisition systems, I think we used from Lunix Technologies an LX M100 lunar simulator, just a basic engineering grade.
Any more questions? No?
All right.
Okay. There's one.
Thanks for the talk. Could you just speak to the limitations of the scalability again?
So in the concept that we currently have, it's incredibly discrete. What you have is an acquisition system that then deposits it discretely into a pre-processing system which conducts its own processes. Then that goes into a reactor, which is then sealed. It's a process which involves multiple discrete elements. So first of all, that inhibits some sort of continuous processing. But secondly, I think that the actual configuration, not only the electrodes themselves, but the internal configuration of the hot zone itself, I think is not particularly scalable. Also, the materials that we've chosen for this particular project are not suitable for long-term reliable use. Does that answer the question?
Yes, and what would have to change to make it more scalable?
We're looking at a couple of scenarios at the moment. I think identifying, firstly, suitable materials that can last the distance, but also identifying a concept of operations that can handle the various pressure gradients throughout the system, from getting raw material to producing pure products. There's a number of significant pressure and temperature gradients that you must overcome. Trying to find a smooth transition between those, I think, is one of the keys to developing a continuous and sustainable, scalable process.
Okay, thank you.
Sure.
Thank you very much. Just a word of caution, a demonstrator is not the beginning of a plant or a pilot plant. Whoever thinks that needs to slightly change the approach, not because it's not feasible, but clearly, as our Tyler said, when you scale up, you deal immediately with kinetic that is different. You have energy gradients that are substantially different, and the way you deal with them cannot be the same as you do in small scale. That's why in chemical engineering, you usually start with the plant, figure out what is your pilot plant, and do the experiment that then teach you how to do the pilot plant and work backwards. Just a word of caution. Thank you very much.
Anyway, thank you so much.
One request, please visit the poster sessions. There are so many interesting posters, and please vote for the posters you like the best. You can do so at the reception. Thank you very much for being here. Thank you very much for listening to our speakers. The session is now closed. Thank you very much.